Hi guys, I'm Shreyas and I will be moderating today's recitation along with Meng, and we will be looking at recurrent neural networks and its architectures. By the end of this recitation, we expect you to understand why RNNs are important, even though we have feed-forward networks. We will go through working principles of RNNs. We will also understand how PyTorch implements LSTMs, and we will also cover the variants of these RNN models. For better understanding, we will also explain the working of RNNs from a perspective of graphical models and cover normalization and dropout. We expect that the knowledge you gain from this recitation will help you get started with homework 3, but we still expect you to do a lot of studies on your own, as these are just the basics of RNNs. And of course, in future recitations, we would cover more advanced concepts and provide you with more guidance in solving homework 3 and homework 4. So one could ask, why do we need RNNs since we already have MLPs or feed-forward networks? Well, in so many tasks, as we would see shortly, there is always a need to remember previous information in order to decide or predict what is coming next. Feed-forward networks are not effective in remembering past inputs. They focus solely on spatial information of the current input and use that to make decisions. RNNs, on the other hand, are designed to remember or store information from previous inputs. It allows them to make use of context and dependencies between time steps. For sequential data, the temporal information which connects the data is more important than the spatial content of each individual frame, which is why we subscribe to RNNs. RNNs have a way of modeling temporal information for these kind of tasks. RNNs have what we call hidden states that act as memory for storing previous information. Now, what is the sequential data that we're trying to learn from and predict on using RNN? Sequential data are streams of input data where you have one input data point dependent on another input data point. It's the kind of data where previous input plays a crucial role in determining the next input. For example, in texts or sentences, the current word to some extent determines the next word or the next set of words. Same with speech, we have word stress and pitch variations, which are expected to follow a certain tempo while speaking. Even when analyzing videos, each frame in the video is sequential, so the model will need to store information of the previous video frames to predict what action comes next. We also have the common time series data, such as stock prices and weather data. We understand that for all these types of data, one needs to have information about the previous input to potentially predict the next set of outputs. So where are these RNN models applicable? RNNs are used under the hood of so many applications, such as stock price predictions. Some of you might be aware of trading bots. RNNs are also used in machine translation and speech recognition system, where context is important in transcribing words or translating across different languages. They're also effective in video tagging and image captioning. Some research has also shown that RNNs are good text summarizers, as they're able to understand passages and create summaries of them. Now, the kind of RNN we might consider to use for a particular task is dependent on the structure of the data. We know most feed-forward networks map one input to one output. However, such constraints are not placed over the RNN network. Instead, their inputs and outputs can vary in length, and different types of RNNs are used for different use cases. For example, we have the one-to-one RNN, which is known as the vanilla network, generally used for machine learning problems where we have one input and one output. Here we have one input image and one output, which tells us whether the animal in the image is a dog or not. We also have the one-to-many network with one input image and a series of words or sentence as output. The one-to-many variant is a common use case for image captioning. There's also the many-to-one network, which is used for sentiment analysis. For example, a customer review has many words or sentences, which is many input, and our model just tells us if it is a positive or a negative review, which is one output. There is also the many-to-many variant used for machine translation, that is transcribing from one language to another, which would have many inputs and many outputs. You can also use the many-to-many RNN for object tracking. Now let's look at the structure of RNNs and how they actually work. We have established that RNNs save temporal information. However, for them to do so, they need to have access to the previously processed information and use this in their prediction. The RNN achieves this by saving the output from the previous hidden layers and passing it as input to the next layer, including the original input X to predict Y. That is why the RNN network is often referred to as a looping network. The hidden layer H in an RNN is equivalent to many hidden layers in an MLP compressed together. Now, this concept informs the notion of shared parameters across hidden layers in each time step. So each hidden layer has a standardized activation function, weights, and biases that are shared across the nodes of that hidden layer. Now, in learning the weights and biases of the network, the RNN leverages a technique called backpropagation through time. This method is similar to the conventional backpropagation in that model learns by calculating errors across parameters from its output layer to its input layer. However, backpropagation through time differs from the normal backpropagation in the sense that it accumulates or sums the error in each time step since the parameters of each time step are shared across the network. So this is an unrolled version of the RNN network. Here we can clearly see that the output of previous layer forms a part of the input of the next layer. These hidden states act as the memory of the RNN network. Remember, the middle layer or the state H can consist of multiple hidden layers, each with its own activation functions, weights, and biases. RNNs often run into two major problems during backpropagation through time, as the weights and biases are being updated, and sometimes this makes them hard to train. One of these problems is the vanishing gradient problem, which occurs when the gradients that carry information across the network become small. And with further update of these gradients, they become even smaller until they become insignificant and lose all information. At this point, the network no longer learns. We can potentially solve this problem through careful weight initialization, choosing the right activation function, and by using LSTMs, which are long short-term memory networks. We will discuss LSTMs in detail shortly. The other problem is the exploding gradient problem, which is the opposite of vanishing gradient. This occurs when the model's gradients tend to grow exponentially and become too large, thereby making the model unstable. In this case, the gradient continues to grow very large until it is finally represented with NAN values. We can use identity initialization and gradient clipping to try to mitigate the exploding gradient problem. Generally, to avoid these gradient problems, we need to decide the amount of information that we need to retain for prediction. So first we examine the classic LSTM. Like we discussed earlier, the LSTM has gates, and there are three of them to be specific. And each of them perform a certain function in the LSTM module. The forget gate is a sigmoid function of the output from the previous layer and the current input. This gate decides which information to omit or forget in the current time step. There is also the input gate, which decides which information to let through in the current time step. Then finally, we have the output gate, which determines how much information that currently resides in the memory makes it to the next layer as an input. Across these gates, there are also different variables that are being calculated as shown by the equations on the bottom right. The combination of these gates allows the LSTM to retain important information from long sequences and discard irrelevant or outdated information. The peephole LSTM is similar to the classic LSTM, but the only difference is that the sigmoid function, which performs the gate operation, does not just consider the output from the previous layer and the current input, but also considers the current cell state to decide which information to retain. Intuitively, it makes sense for the cell to know what information it currently has before updating this with the new information. Now let's discuss another variant of the RNN, which is called gated recurrent unit, or GRU. This has a simpler structure compared to LSTM and allows for fewer computations. In contrast to LSTM, which has three gates, a GRU has just two gates called the reset and update gate. It also has fewer number of variables to be computed compared to the LSTM, so we expect the training time using GRU to be lower than that of LSTM. Let's see how the GRU works. The gate RT is known as the reset gate, and it enables us to control how much information from the previous state we want to retain. The GRU combines the input and output gate from the LSTM to form an update gate. This is represented by ZT. This determines what information to keep from the previous hidden state and the current input. The final output of the GRU, HT, then considers what proportion of the previous state to retain and adds that to the useful information in the current state. We see there are fewer equations and computations compared to LSTM, and you also get comparable performance. In fact, in some cases, GRU works better. But one of the cases where GRU lacks in performance is unbounded counting. This is because in this equation, you can see that we're using the tan h activation function. This bounds the value of ht tilde to between -1 and 1. That's why GRU finds it difficult to perform unbounded counting, whereas this is not the case in LSTM since it is not bounded. We have another variant of RNN, which is called the bidirectional recurrent neural network. This uses future data for making predictions at the current time step. As the name suggests, within this RNN, we have two networks, a forward network and a backward network. The forward network is represented by the network at the top of the block, and it processes values from time 0 to time t, while the backward network, which is at the bottom, processes the values from time infinity to time 0. The final output of the block will be a function of both the forward and the backward network. Typically, we concatenate the output of these two networks to form the output. But alternatively, we can aggregate them as well by either summing them or finding the mean of both outputs.
Hi guys, my name is Bone. In the next few slides, I would like to present you another perspective to view recurrent neural networks, which I found to be quite interesting. This was actually briefly covered during lectures, but I would like to talk a little bit more about this during recitations. So before we dive in, let's first recall hidden Markov models. So in HMMs, we have a sequence of hidden variables, H, and a sequence of observations, X. If we remember this, the most important assumption in HMMS is the conditional independence, which means, for example, given the current hidden state, the current observation is independent of all previous hidden states. And another thing to notice here is that the hidden variable H is discrete. So if we draw hidden Markov models as a graphical model, we will have a figure something looks like this, right? And so for hidden Markov models, it was very popular for sequential tests, probably like 20 years ago. And while nowadays people are just switching to those fancy recurrent neural networks or transformers. After reviewing hidden Markov models, we can discuss a little bit about state-space models. So for state-space models, it's actually just a continuous version of HMMs, which means it has a continuous variable for all of the hidden variables in the graphical model. But it turns out that it's actually a little bit more complex than it sounds like. It has a lot of implications. For example, we will have different inference algorithms. And a specific instance of SSMs is called linear dynamical system. So we have two equations. The first equation is given the previous hidden variable, how do we get the next hidden variable? So W here is a noise term, and A here is a matrix. So this is just a counterpart of the transition matrix in hidden Markov models. And we have another equation, which is our observational model, which is given the current hidden variable, how do we get our current observations? And C here is another matrix, and V here is another noise terms. typically people solve such kind of systems by making Gaussian assumptions. For example, people would assume the hidden variable to be a Gaussian distribution, and at the same time, people also assume the noise terms to be Gaussian. And in this way, based on some properties of the Gaussian distribution, for example, if we have a joint Gaussian distribution, then the conditional and marginal distribution would also be a Gaussian. Based on such kind of properties, people would derive different kind of inference algorithms and learning algorithms to solve linear dynamical system. So now we have these two equations, one for the transition relationship, and another for the observation relationship. And by having these two, we can imagine an estimator of the true hidden variables, right? We will take in the hidden variable in the previous time step and the current time steps observation. And we have A prime and B prime, another two matrices. And we estimate the hidden variables by having these two input. And it's still linear. By the way, it's also called the famous Kalman filter. So you can see that the formulation here is pretty has been pretty similar to recurrent neural networks, right? So if we imagine, what about, let's say, instead of linear relationship, what about having a nonlinear estimator, right? We take in the hidden state of the previous time step and the input of the current time step, and we take some kind of nonlinear functions. Let's say, let's say we add some activation, nonlinear activation functions. In this way, we actually get recurrent neural networks, right? Does that sound interesting? By having these this kind of derivations, you can see the connection between the popular recurrent neural networks nowadays. You can see the connection between RNNs and the kind of old school hidden Markov models. So now let's briefly discuss about applying normalization and dropout to recurrent neural networks. So based on your previous experience in homework P2s, you probably have already realized that adding normalization layers to deep neural networks is very important. It helps convergence, it helps vanishing gradients, it helps everything. And let's imagine if we would like to apply batch normalization to recurrent neural networks, we actually would have a lot of problems. So the most obvious problem is that the statistics could be different for different time steps, right? And it also turns out that using batch norm to RNNs in an obvious way typically does not work well in a lot of different settings. Here I listed two papers that successfully use normalization for RNNs. And I briefly highlight the key ideas here. So for recurrent batch normalization, they will have a separate batch norm for the recurrent term and the input term. And also they will have separate statistics for different time steps. But yeah, you can imagine it still cause trouble, right? What if the length of the test data is longer than all of the training data, right? In this case, you don't have any statistics for the later time steps. So the practice in that paper is to just take the longest possible statistics in the training data, but you can see it's still not satisfactory. And also, as shown in the paper, the initialization of the gain parameter also matters a lot. And another paper is the famous layer normalization, which you have probably experimented with in your homework P2s. So layer norm was originally proposed for addressing the difficulty of applying batch norm to RNNs. But nowadays, it's actually still not very common to apply layer norm to recurrent neural networks. But layer norm nowadays, is widely used in a lot of other scenarios, like in transformers and convolutional layers. So you can see that applying normalization to recurrent neural networks is actually not an easy problem. Now let's briefly discuss about applying dropout to recurrent neural networks. So before we do that, let's first think about the two types of connections in RNNs. Yeah, so you can see in this figure, we actually have only two types of connections. The first type is the layer-to-layer connection, right, like the green arrow here. And the second type is the hidden-to-hidden connection. And we only have these two. So now let's think about the LSTM implementation in PyTorch. We actually have an argument called dropout here. So by setting this argument, we actually only applies the dropout mask to the layer-to-layer connection, which is the colorful one in this figure. And this is the most common practice for people to apply dropout to recurrent neural networks. So the reason behind this is typically concluded in literatures that because for hidden-to-hidden connection, if you apply dropout here, you will mask different positions in different time steps. And this will lead to some kind of instabilities. So yeah, in this way, people typically only apply dropout to layer connection, which means if we set the number of layers is equal to 1, this dropout argument will take no effect at all. This brings us to the discussion about variational RNNs or locked dropout, as we will probably use in homework 3 or 4. So the key idea motivated by the problem described before is to keep the dropout mask fixed, which means we use the same dropout mask in different time steps. And you can see the difference between these two figures. This is a naive dropout recurrent neural networks as implemented in PyTorch. And this is variational recurrent neural networks or locked dropout, where the same color means the same dropout mask, and you can see the dropout mask for different time step remains the same. And I also list the corresponding paper here. But you probably want to note that the implementation in Torch NLP is actually slightly different from what is described in that paper. The implementation in Torch NLP implement locked dropout only for layer-to-layer connection, but the position is fixed in this case. In the final part of this recitation, we would like to give you a demo about using recurrent neural networks as a language model for Shakespeare's text. Now let's dive into the character level language model for Shakespeare's text. So before we get started, I would like to mention that nowadays the cutting edge language model will typically not at the character level. Instead, they will be trained at the token level, which means a single token would contain multiple characters instead of just one character. So the difference between the two is that for character level language model, you have a much smaller you have much smaller space. Like for English, you only have 26 letters. But in English, you can imagine you will probably have like millions of unique English words, which gives you a much larger space. And, but the advantage of token level language model is that you can capture the relationship between different tokens. While for a character, it's hard to capture some obvious correlation between, let's say, A and B. There's just no obvious correlation to capture. Yeah, so let's dive in to our character level language model example. Here we just load necessary libraries. And here we do some exploratory data analysis. For example, we print the first 203 characters and the last 50 characters. And we can see on this dataset, we have 84 unique number of characters. And we print out the first 17 characters. Here we define our dataset. So I assume that by now you should be pretty familiar with this kind of workflow. Before we dive into training, we will need to define a dataset class and the data loader to load our dataset iteratively. So I would like to mention a few things for the dataset here. So firstly, we have defined a sequence length. So the purpose of this argument is to split the whole dataset into different parts. And each part we have 200 characters. The reason behind this is just for convenience. We want to make sure that each data point within a batch have the same length. But as you will see in later homeworks, this assumption could break. And in some tasks, we have to handle variable sequence lengths within each batch. And you will see how we are going to do that. And another thing to notice here is that we have a shift for get item, which is because for a language model, we are trying to, given all previous characters, we are trying to predict the probability of the next character. That's why we have this shift here, because our target is the next character of the sequence. And we have this collate function for creating a batch. And now next we define our character level language model, which is simply an embedding layer, an LSTM layer, and a linear layer for output. Here, the size of a vocabulary is just a unique number of characters in our dataset, which is 84, as we have seen previously. And this is the embedding layer, which is to convert an index of the 84 character vocabulary to a dense vector. And the dimension of this vector is defined by this embedding size. And then we have an LSTM neural network that takes in the embedded vector and output, produce a hidden state output. And we have a scoring, which is just a linear layer that takes the hidden state of our LSTM layer, and then produce a prediction for at the space of our vocabulary. And we also define a generative function, which takes in a sequence and trying to produce next n characters. So what this function does is we take in a character, and then we let the model produce the output probability, and then we take the max over all of the vocabulary space. And then after we generate one character, we just keep going. We just input this generated character to the next time step, and then we produce n characters. And this is our train function. You should be pretty familiar with this from your homework P2 experience. It's mostly very similar. Yeah, and we start training. You can give it a try. We can see a demo here. So to be or not to be, that is a queue, and we ask the model to predict the next 8 characters, and we get question. Yeah, this is kind of satisfactory because it's a famous text from Shakespeare, and we did it. Yeah, I think this comes to the end of this recitation, and I hope you enjoy it. Thank you so much for watching.